Hi, everyone. My name is Somaya Sadat. I'm the Assistant Director at the Center for Analytics and AI Engineering at the University of Toronto. It's my pleasure today to welcome you all to this seminar, the joint seminar with the University of Seoul. The topic of the seminar is the challenge of speaker recognition and spoofing detection. And our speaker today is Professor Ha-Jin Yu. Just a bit of introduction on Professor Yu. He received his undergrad, master's, and Ph.D. degrees in computer science from KAIST in Korea in 1990, 1992, and 1997, respectively. From 1997 to 2000, he was a senior researcher with LG Electronics. From 2000 to 2002, he was a director with SL2 Ltd. Since 2002, he has been a professor at the Computer Science Department at the University of Seoul. His research interests include speech and speaker recognition, acoustic scene classification, and machine learning. He is the editor of the Journal of the Acoustical Society of Korea and the Journal of the Korean Society of Speech Sciences. With that introduction, I'd like to ask Professor Yu to start his presentation. Thank you.
Thank you for the introduction. And I am so excited to be here, and I'm very honored to be here. Today's my talk is the challenge of speaker recognition and spoofing detection. The spoofing means deepfake voice. So the people can make fake images. So also the people can make a fake voice. So the detection of such deepfake voice is also a topic of this talk. So speaker recognition means from your voice determining who is speaking. So this can be used in security systems like personal identification and confidential information retrieval and accessing to classified area and files and something like that, computers and internet banking or shopping, and taking meeting minutes and searching or indexing multimedia materials. So if you want to search for a special person in a movie, you can find it using the voice, or prisoner surveillance and personalization of your devices like your car. So you can adjust your mirror, something like that, and in marketing. So it can know who is speaking, who is speaking, and the gender, the age, etc. So the speaker recognition can be classified into two categories by the recognition type. One is speaker identification and one is speaker verification. So speaker identification means we have a lot of lists of people, and if the system hears a voice, he can select who is speaking among the group of persons. And the speaker verification means that it is used as password. So I provide my ID and my voice, then the system can accept or reject my voice, like typing your password. The speaker recognition also can be classified according to the text dependency. So it can be divided into text dependent and text independent. So text dependent means every time I use the system, I use the same password, like Open Sesame. So it is fixed, but it is a danger of attack because someone can record your voice and play it, then he can pass the security system. And text independent means that it can recognize any sentence spoken. So while I'm speaking something else, other than the password. So while we are having conversations, the system can know who is speaking. So it is more complicated than text dependent, but it has more convenient. Yeah, so it can recognize your voice background because it can recognize your voice while having other conversations. So if we have a lot of speech data, then we can build a speech recognizer and speaker recognizer. So the speech include many words or many speakers. So if we group the speech according to the words or phoneme, then we can build a word model. Then we can build a speech recognizer. And if we collect the speech, if we group the speech according to the speaker, then we can build the speaker model. Then we can build a speaker recognition. So to recognize human voice, first we have to extract some features for the machine learning. So we say that there is acoustic features. So we extract acoustic features from an input speech signal, and the speech is have variable size. So we divide the speech into small segments of fixed size. So we divide the speech and we call it a frame. So a frame is usually 25 milliseconds length long, and so if we divide the speech into segments of 25 milliseconds, then we have many segments, and from the segment we extract acoustic features. So if we have a long utterance, then we have many feature vectors. Okay, so the features usually filter bank coefficient, and or the famous one was male frequency capture coefficient, which is the modification of spectrogram. So spectrogram looks like this. So you may see the waveform here, and if we transform using Fourier transform, then we can get the spectrum. And if we see this picture, then we can see that what word was spoken, and or we can see that whose voice is this. But it's not easy for human to detect or discriminate such information, but machine learning can tell the difference. Okay, so human articulators has various forms. So we have tongue, and we have lips, teeth, and nasal cavity, and these paths act as the resonator. So from this structure, the voice is produced, and the resonance status, the frequency characteristics change according to the shape of the articulators. So we can discriminate the words, and we can discriminate the speaker. So we can see whose voice is this. So as general machine learning, it has this is a binary classification problem. So usually we have input of the utterance, and we have front-end processing. So we can get the acoustic feature from the speech, and we have two models. One is hypothesized speaker model. So this is the model for user, and this is a background model. And we calculate the likelihood of two models and we compare the two likelihood. So we call this score. So we usually calculate the ratio of two probabilities. And if we use log probabilities, then we can use the difference. And if the difference is greater than the threshold, then we are accepted. If the score is lower than threshold, we are rejected. So this is a general machine learning problem. And the measure of the performance is not easy to determine because there are two errors there. So the miss or false rejection errors, the error rejecting target speaker, and another error is errors accepting imposter. That is called false alarm, false acceptance. So if we have higher threshold, then there are many rejecting target speaker errors. If we have low threshold, then there are many false alarms and false acceptance. So the performance changes according to the threshold. So we have a measure called equal error rate. That means that we have a threshold that make the false rejection error and false acceptance error the same. So in this point, the two errors became the same. Then we say that this error is equal error rate. Also, there is another measure for speaker recognition. So this means minimum detection cost function. So the cost of the error is different. So in some cases, if we accept the imposter, the false user, then it costs much. And some point, in some other cases, if we reject the user, then also we have to pay some cost. So we set some cost for missing and false alarm, and we calculate the probability of target and non-target, and the probability of errors, missing errors and false alarm errors. So we multiply those values and we calculate the evaluation metric. So there are two metrics for evaluating speaker recognition. And we have many public data, and one of the famous one is NIST speaker recognition evaluation. So this is American National Institute of Standard and Technology. So in this institute, it has many competitions once every 2 years. So they collect data using the telephone or microphone speech or smartphone, and with hundreds of speakers, and the amount of speech is thousands of hours, and we can purchase the data. And also there's another set of data which is called VoxLab. This speech is collected from YouTube. So there are many celebrities, about 7,000 celebrities. The voice of 7,000 celebrities were collected, and more than 1 million utterances. So this is a realistic voice. So and we can build a speech recognizer of the voice of the celebrities. And these days, the error rate is less than 1%. So sometimes it's about 1.5%. So there have been many ways to extract the features from the voice. And as in usual machine learning, the Gaussian mixture model was used for a long time. but these days we are also using deep learning. So the recent most famous feature is which is called X-vector, and this uses the deep learning model which is called time delayed neural network. So this is a very old model for dealing with sequence data like a speech or music or a signal, and then there are many layers of time delayed neural network, and this is applied for each frame. That means each segment of the speech, and then after that we have a step called statistic pooling. So this pooling is similar to pooling in CNN, and the statistics means average or something like that, the statistical values. And then we have another layers, and so the final output is speaker identification, so a speaker ID. So if using the input segments of speech, it calculates speaker ID, and this is trained to maximize the probability of the user. And before the final layer, so the output of the hidden layer is used as the new speaker feature. So we say that this is embedding. So actually embedding is used to represent words in language models. No, so we say that this embedding is the feature. So we have variable length of utterances, and the embedding is a fixed side. So this, we say that this is segment level. So this means that if no matter what the length is, length of the utterance, we have a one embedding of fixed size. Then you can compare the embeddings and calculate the score for each speaker. And also, attention mechanism is used in here. So these days, ChatGPT is very famous, and attention is main principle of GPT, and it is also used here. So instead of statistical polling, after the first few layers, we use attention to the features, the frame features. So the attention is used to select which segment is the most useful part. So in our utterance speech, there are some parts. Some parts is useful for discriminating the idea of the speaker, and some parts is not. So the attention selects the important part of the speech, so that we can select the person who has the highest score. So I think many of you know about the attention mechanism, which is used in language models and very famous. And the state-of-the-art famous model is this model. It emphasizes channel attention, propagation, and aggregation of in TDNN based speaker verification. So this is very famous and used in many researches as baseline. So it has squeeze and excitation network block. So and it uses famous resonate block. So this means that it squeezes So the input is squeezed into small part and then expanded again. So, and it has many of these blocks, and it has also attention block and fully connected. And the key point here is that there are many layers, and the output of many layers. So the layers close the input and layers close the output is collected and concatenated and used as the feature. So the layers in earlier stage that is close to the input means that it has more detailed feature, and the later layers, which is closed output layer, is more abstract. So it collects the detailed features and abstract collect, and then it has the pooling that aggregate all the information, and finally it decide the ID of the speaker. So there are many challenges of speaker recognition. There are many noise. If there are many noise in the speech, we cannot recognize the voice. Or if the utterance is too short, like if I say a long 10 sentence, it is easy to identify who is speaking. But if I speak only a short word, then it's not easy to select the person. And there are also deepfake problem. We say that there is a spoofing attack, so we can make deepfake images using generative deep learning models. Also, we can generate good high quality fake voice using deepfake model. So these days, the deep learning has very good ability to generate such things. So detecting the deep fake voice is also very important. So the basic principle of separating speech from noise is also using DNN. So if we have a speech with noise, then the deep learning DNN can generate clean speech. Okay, and then in more detail, we have a speech with noise. Then we have two models. One is to recognize speaker, and then one is to recognize the noise. So we train two different target. So one target is speaker recognition, and one target is noise recognition. And then the feature of speech and noise can be divided into two. One is one feature for speaker information only, and one feature for noise recognition, noise information only. And then we wish that if we combine two features, then we can get the original noise speech input. So this is our work. This is done by my student, my former graduate student, Mr. Jung, and many other students. And I want to give this credit to them. And the key idea here is that instead of traditional spectrogram or filter bank or many other human-made features, we use only deep learning. So the speech input is input to deep learning models. So this can be any deep learning models currently in the earth. So we may use convolutional neural network or RNN, LSTM, or fully connected. So the first part mainly is convolutional neural network or time delayed neural network, like recurrent neural network. and the final part is fully connected network. So this is a simple introduction of our approach, but there may be many approaches using attentions or something like that. And current work is we are using UNet. So UNet is used for image processing. So it has this shape of U shape, and there are many layers in the U shape, and there are many connections between the levels of the layers here, like this. And we added one more path here. So it has a U-shaped neural network here. So the information from the very primitive features can transfer to the later layers of the this part, and also there can be another part. So the first part enhances spectrogram, so it reduces noise, and then the final goal is to detect the human voice. And so, as I mentioned before, there are the problem of deepfake voice, deep voice. So there is a challenge called automatic speaker verification spoofing and countermeasures challenge. So it detects the spoofing. So there are 3 tasks. One logical access is detecting the attacks using the text-to-speech and voice conversion. And another is physical access, which means recording. So if you record my voice using a recorder and you play it, then the system can the recorder can pass the security system. And the third one is deepfake task. So this task use compressed audio similar to the previous task, but without the speaker verification. So there are many ways to get a fixed side feature from the variable length features, like using recurrent neural network, or we can use statistics like average or something like that, or we can use attention. So, and the final one is we are using graph attention networks. So the graph neural network is used in many fields, such as social network. So the social network, we can make a graph of person, and we can classify the persons in the network, or we can classify the relations between the persons, or we can classify the graph. So the graph neural network is widely used these days. So we can use graph neural network to extract features from the speech. Also, there are graph attention network. So it applies attention mechanism to the graph neural network. And so there are many nodes, and this node has many relation between other nodes, like these one, and we can calculate attention weights. So and then finally, using the attention, we can decide that this node has high relation with this node. So I want to talk about briefly about the system, which is built by my former graduate student and other researchers in Eurocom and Naval Corporation. And I want to give the credit to them, their hard work. So the motivation is to that spoofing artifact, which means that the key point in the speech that can verify the human or detect the fake voice is something in the time scale features or in the frequency scale features. So we extract spectral and temporal representation, and we can make two graphs using the two representation. So this is the total framework of the system. The first speech input is encoded using many ways, like traditional spectrogram or many other deep learning methods like CNN or RNN. And we have features, and we divide the feature into two. So the sequential, time, and spectral domain, and we built two graphs, and we combine the graphs using another link, and then we have attention graph attention networks and two layers of graph attention networks, and there are two paths, and we get the maximum of two paths, and then we collect the information from the graph using pooling, many kinds of pooling like maximum or average, and then after that, using some fully connected layers, we can get the output. The output is the binary output, spoofed and bona fide, which means the good real voice or deepfake voice. Okay. So the input is 4 seconds raw waveform, and encoder was RowNet, which is introduced before, I mentioned before, using getting the waveform of speech and then using some CNN or RNN. So this is the model encoder, and we have two graphs. So spectral and temporal. And we have two graph attention network and graph pooling layer. So the low waveform is processed by the sync layer, which is these are the collection of filters trained by deep learning. So usually, traditionally, we have used Fourier transform to convert the time scale speech into frequency scale, but these days we use deep learning to transform the input waveform, and then we have this feature. It has many channels and two axes, time and frequency, and we get the maximum along the frequency and maximum along the time, and then we can get two types of features. And with that, we make two graphs. And using this graph, we apply attention and graph pooling mechanisms. So we combine two graphs, two kinds of graphs using the layers, and we have two paths here. So it has two processing paths. It has identical structure, but it is trained differently. So the two paths has different weight, and they have different results, and we get the maximum of two results. So this means that we divide, we process the input with two different methods. Then this part has some key to discriminate the deepfake voice or the voice ID, and this also has some, and we maximize the two results. Sorry. Then we get the maximum of two results. Then we can get many the more key points for the discrimination ability. Okay. And then the readout means that we can get the final result from the nodes. So we use maximum or average or stack node, which is the collection of all the nodes. So the stack node here is a collection of the information of the nodes in the graph. So the graph attention mechanism and graph pooling mechanism is borrowed from the graph neural network community, and it is applied to the speaker recognition, and we get a good result. So we use ASV spoof 2019 data, and we have we compare this with many other systems, earlier systems, and it has the lowest cost, lowest detection cost function. Okay, and the number of parameters are smaller than other systems here. So this is the proposed system, and this is a light version of the system, and it has less parameters, but also the performance is better than others. So the detection cost function is the lower the better. So it has, this is the best, and this is the second best, the light version of this system. And also there are many kinds of attacks. So for example, many different kinds of recorder, different kinds of synthesizer or converter, and in many of the attacks, many kinds of attacks, the proposed system has lower error rate. And after that, finally, I want to introduce to you the latest model, which is also proposed by my former student and the researchers in Eurocom. So the key interesting point is that we are using pre-trained self-supervised model. This is also used in ChatGPT. You know, I think many of you know about the ChatGPT, and the GPT means generative pre-trained transformer, and this is also that kind of thing. So pre-trained transformer. Also in GPT, they use self-supervised model. Okay, so we are using the same principle, same mechanism of GPT, and we are having the best performance. So I think it's amazing. So the same principle is applied to both the language model and speech. Okay, so there is a model using wave-to-back-to model. This is kind of pre-trained self-supervised model, which is huge, a large model. And as a result, it delivers up to 90% relative improvement in 2021 competition. So the later part is the same, but only difference is that the front part. So this is the former system. Okay, so we have been using the front end using deep learning, and this is replaced by transformer. Okay, you know, many of you know about transformer. So a transformer is used to train the language model, and it is also can be used for training the speech. Okay, in speech recognition, they use transformer. So when you train a language model using transformer, you delete one word in the sentence and train it, and also it deletes one part of the speech and use a transformer and masking, and then you can train the system. Okay. So this is overview of the front-end system, wave to back system. So this is almost the same as transformer. Okay, instead of the text, instead of sentence, we use the speech as input. Okay, and they also use some attention mechanism, modified attention, using also to the sequential time scale and spectral scale, and the error was reduced greatly. Okay, 90% relative improvement. So the challenge of 2021 is more hard than before. So error was higher, but it is reduced drastically using the a pre-trained self-supervised large model. Okay. So it also has greater performance, smaller error with all other all kinds of conditions. Okay. And last year, we organized a challenge that is called Spoofing-Aware Speaker Verification Challenge. So until now, the research on speaker recognition and spoofing detection, that means deep voice, deep fake detection. And this challenge, we combine the two. So we have a challenge that combines the two systems, and the system has to detect the speaker of the voice, and also it has to detect the fake voice. Okay, so it has the baseline is some fusion of the two systems. Okay, one is speaker recognition system, and one is countermeasure system. And so we finally collect the two scores, the scores of the two systems. And then second baseline is we have two systems, and by combining them, we have a feature that can also both discriminate the speaker and also the genuinity of the speech. Okay, so spoofed or real speech. Okay. So I will conclude my talk here. So, so one of the most important things in speaker verification and defect detection is to get a feature vector of fixed size from the input of variable length. Okay, so there are many ways, like using recurrent neural network or statistical pooling or graphed neural network. And we have investigated many of the approaches. Okay, and research current trend is using large pre-trained self-supervised models like GPT. Okay, so the GPT was trained using a lot of sentences, and it can be used many tasks like question answering or summarizing some text like that. So we can use the big pre-trained model to speech recognition or speaker recognition or defect detection. So this will conclude my talk here. Thank you very much.
Thank you very much, Professor Yu, for a very interesting seminar. I'm sure everyone enjoyed that, and this is such a timely topic. If anyone has any questions, please feel free to type them in the Q&A box. We have a few minutes left and we can get them answered. I know this was a lot to process, so some people may need to watch the recording again. Are there any questions that you'd like to ask? I think I will stop the recording, but we can stay on for another 2 minutes. If anyone has anything to share, we'd be happy to stay on. Thanks again on behalf of myself, CARTE at the University of Toronto, and our colleagues at the University of Seoul. Thank you very much for attending this seminar. And thank you, Professor Yu, for such a nice presentation. Thanks.
Thank you very much.